This is Aya Mohammed Hassan Mukhtar with the matrix 251060169-1, who will be talking about the mechanical part of the project. When evaluating existing assistive devices in the market, a glaring user experience issue stood out. You, most Almost all of them force the user to wear a specific article of clothing. This severely restricts its user's personal style, comfort, and independence across changing social or weather conditions. To solve this, my project pivots to a highly versatile clothing independent form factor, a compact 4 to 7 centimeters smart batch which can securely clip into a winter jacket, a summer shirt pocket, or a back strap without shifting weight balances or causing discomfort. Power budgeting and architecture. One of the biggest challenges in compact wearables is balancing battery life with physical bulk. To achieve true operational autonomy without creating a massive device, I engineered a hybrid power scheme that utilizes two distinct energy sources. For primary power replenishment, the device features an internal ensured long-term engineering reliability. I implemented a hardware backup system, which is a dedicated USB Type-C port is integrated onto the side wall. For daylight energy harvesting, I integrated a 60 by 30 by 3 millimeters polycrystalline solar panel onto the upper housing of the cover. Our active internal electronics draw a combined continuous load of 0.9 watts, which translates to roughly 180 milliamperes at 5 volts, while our compact solar panel generates a maximum of 0.25 watts under direct sunlight. Its inclusion is mathematically justified as a trickle charger. It directly offsets the battery discharge rate, effectively expanding the continuous outdoor runtime from 5.5 hours to 7.7 hours when paired with the internal 1000 milliamperes hour flat LiPo battery. The top cover was modified with a 30-degree sloped roof to orient the solar panel optimally toward incoming sunlight during outdoor locomotion. I then applied smooth 4mm edge fillet to ensure an ergonomic, snap-free shape that safely slides against fabrics without catching. Using the shell tool, I generated a uniform 2mm wall, assigning the physical material properties of plastic ABS to guarantee an impact resistance. Lightweight structural shell, the remaining raw internal space inside our shell measures exactly 6.6 by 6 by 3.6 centimeters. Ultimately, this project provides invaluable experience in true mechatronic system integration. I moved far beyond basic 3D modeling and learned how to balance competitive electrical loads against strict physical envelopes. I gained a deep understanding of standardizing industrial drawing layout within the Inventor DWG environment, especially managing global textile heights, row dimension scales, and tolerance padding to ensure a digital CAD file that actually be manufactured cleanly in real world. By treating the circuitry and the plastic casing as a single code-dependent system, we successfully delivered an assistive device that prioritized in true mechatronic system integration. I moved far beyond basic 3D modeling and learned how to balance competitive electrical loads against strict physical envelopes. I gained a deep understanding of standardizing industrial drawing layout within the Inventor DWG environment, especially managing global textile heights, row dimension scales, and tolerance padding to ensure a digital CAD file that actually be manufactured cleanly in real world. By treating the circuitry and the plastic casing as a single code-dependent system, we successfully delivered an assistive device that prioritizes both rigorous engineering and genuine user empathy.
Good morning. My name is Dua Babakir Ibrahim Mustafa. My matric number is 251060325-1. Our project is focused on total accessibility, and this entire power management section of the electrical circuit was designed with critical engineering reasons in mind to ensure maximum reliability for impaired users. First, let us look at our main charging source, the modern USB Type-C. We choose this as our primary power source because it provides a reliable, standard, and high-speed way to charge the system indoors, ensuring that device remains fully functional and runs smoothly from the stored battery power. However, as engineers, we wanted to ensure this design with an essential sustainable feature. Therefore, we integrated a solar panel purely as an extra power source. This solar panel provides an excellent, clean, and healthy way to harvest pounds embedded energy whenever the user is walking outside under the sun. By catching this extra power on the go, the solar panel activity strains the battery life, helping to protect and extend the system total energy to keep it running safely from 2 to 3 days, even if the user is completely away from a main wall plug. To safely connect these two different power inputs together, we implemented a critical safety feature. The diode placed right after the positive terminal of the solar panel. This diode acts like a strict one-way security gate. It allows the extra solar energy to pass through cleanly, but the moment a user plugs a powerful phone charger into the main Type-C port, the diode instantly blocks that primary high voltage from flowing backward into the solar panel, completely protect the fragile solar cells from reserve's correct destruction. Both of these independent power paths made safely at the input of the TB4056 charger. These chips act like intelligent battery manager, safely regulating the voltage and correct profiles required to charge our lightweight. Now the core electronic in this system require a higher constant operating voltage to prevent system lag or false alarms. To achieve this, the raw battery power is passed into the MT3608 U2 to high actually step up chip as like electrical pump, taking the floundering battery voltage and boosting it up in a rock solid. This clean 5-volt line directly powers the master controller, which is the dual-core ESP32 microchip, the main brain of our project. The ESP32 is constantly executing code in real time, monitoring data coming from the sensor U4, mounting right on the front frame of our hat. While traditional cans only protect a user fit, our IR sensor acts like user's upper eyes, scanning for dangerous head level like tree or open combatants. The exact millisecond an obstacle is detected within the danger zone. The ESP32 brain sends a signal to the ring puzzle hiding comfortably inside the sweet band, giving the user an embedded low audio warning to stop walking. The brain uses its hardware communication lines to stay constant contact with the high touch 4G GSM plus GPS model U6. This model constantly tracks the user exact stillness coordinates, standing completely ready to broadcast a live location link, an automatic emergency SOS text, a message to family members, or if the users get lost or an emergency. Building this circuit taught me a real-life engineering lessons about details, safety, and people. First, I learned that small details matter, like editing the resistor, so modern chargers can actually recognize a Type-C port. Second, I learned to think deeply by using the diode to protect part from user mistake, like charging the device in the sun. Third, I taught me to put the user first. A blind person cannot see which way a plug goes, so choosing a Type-C port and automatic solar charging was about ability, not just spaces. Finally, fixing circuit errors taught me patience and discipline, providing that an engineer must keep testing and ensuring until a design is completely perfect, safe, and ready to build. In conclusion, this circuit design is highly creative and practical because it perfectly balances active user safety with an intuitive, reliable power built around a primary Type-C input and secondary solar system. Thank you. I will show you quickly how I set up my PCB design for our project. First, I created a new board using our project dumbbell and netlets. Then I added the mechanical mounting holes and placed them neatly in the four corners of the board, making sure they are set as non-electrical parts. The second and most important step was arranging the components. At first, all the parts we built up randomly on the left side. I used the components tool to separate them and separate them outside the board outline. I made sure to place the main contours and voltage first, and I rotate the part to keep the green connection lines as net as possible. Next, I move on to routing. I first set the auto route feature since this is a simple project and we want to keep manufacturing costs low. I change the setting to turn off the top layers. This forces the program to route everything on the single button layers. In conclusion, this circuit design is highly creative and practical because it perfectly balances active user safety with an intuitive, reliable power built around a primary Type-C input and secondary solar system. Thank you.